Okay, let's take a look at the gradient of a scalar. Let's say you just walked into an air-conditioned room where your friend is also standing right next to you, and the air conditioner is pumping cool air into the room. Okay, so you walk into this room and see your friend over there standing and turning the air conditioner on, and the temperature of the room is supposed to be cooled down. Okay, but you're feeling that as you enter the room, it's not as cold as you expected. So you ask your friend, "Whoa, it's supposed to be cold in here. Why it's so hot?" And your friend replies that no, it's perfectly cold over here. Why? The thing is, when the air conditioner starts pumping the air into the room, the temperature around the air conditioner goes down faster than it does in the regions away from it. Let's say after turning the air conditioner on, the region surrounding the air conditioner goes down to 26 degrees Celsius, and the region that is further away from the air conditioner is yet to get down to 26 degrees, so it's stuck somewhere around 28 degrees Celsius, and it's waiting to get down to 26 degrees eventually. You're standing in this region and you're not there, but your friend is standing under this region, so he is already there. So the temperature in this room is different. This is called spatial difference of temperature, all right? In the very first lecture of this course, we told you that temperature is a kind of a scalar quantity, right? So as you move around in the 3D space into this room, you are experiencing different temperatures, right? Let's say this is a region where the temperature is 27 degrees. This is a region where the temperature is 26 degrees, and the region farther away is 28 degrees. And outside the room, when you get outside of the room, it's 30 degrees. As you move around in the 3D space, the temperature changes. That means there is a spatial change of a scalar quantity, right? So gradient of a scalar means the spatial rate of change, not the change, but the rate of change of a scalar in terms of space, not time, okay? Let's say you move from this point to this point over here. Let's say you moved 5 feet from point A to B. Point A has a temperature of 26 degrees and point B has a temperature of 27 degrees. So the change of temperature over here is 1 degree per 5 feet, all right? So you get some value like this. Okay, so this is the rate of spatial change of temperature. Now let's say instead of point B, you start from A and move to point C over here. Okay, C is also in the region of 27 degrees, so the difference of the temperature is still 1 degree. You are moving from a region of 26 degrees Celsius to a region of 27 degrees Celsius, so the change of temperature is still 1 degrees, but the distance that you are traversing now is obviously greater than 5 feet, right? It's quite clear from this picture over here. Let's say this is right angle triangle, so obviously the hypotenuse will be higher than the other two arms. So if you're moving from A to B, you have to move a distance equal to 5 feet to get from 26 degrees Celsius region to a region where the temperature is 27 degrees Celsius. So the spatial rate of change of temperature is this. But if you decide to move from A to C over here, obviously you will have to move a greater distance now. AC has a length of greater than 5 feet, okay? So let's for example say it's 7 feet. So this thing will obviously be something that will be less than 0.2 degrees Celsius per feet. All right. So what we can see here is that you get the maximum rate of spatial change of the temperature if you move from A towards B and not any other ways, all right? Because if you move along this direction or this direction or this direction, you'll always have to move a distance that is greater than 5, okay? And when you divide the temperature change by any distance or any length greater than 5, this will obviously give you a rate smaller than zero point 0.2. So for the maximum rate of change, you'll have to move towards the AB direction, okay? So gradient of a scalar basically is a vector that denotes the value of the maximum rate of change of the scalar, and also the direction you have to traverse to get that maximum value. It's a vector, the magnitude of which denotes the maximum spatial rate of change of scalar, and the direction denotes the direction you have to traverse towards to get that specific maximum spatial rate of change. All right. Okay, now let's say if you remember electric potential, just like temperature is also a scalar quantity, right? So let's say this is an equipotential surface, and on every point on this surface you have a potential equal to V1, and this is another equipotential surface that has a potential equal to V1 plus del V. Potential difference of del V separating those two equipotential surfaces. Let's say you're standing over here, the point, let's name it A, and you want to go to a point uh, on the upper equipotential surface. Let's say you want to go over here, which is B. Now, if you follow the AB path over here, you will have to move a distance equal to dl. So the rate of change along AB direction will be del V divided by dl, all right? And now let's say you move along the AC direction to get to the same potential surface of V1 plus del V. So in this case, you move a distance equal to dn. So the rate of change in this case will be del V divided by dn. Now, obviously, from this picture, it is clear that dn is smaller than dl, which in turns means del V divided by dn is greater than del V divided by dl, right? So when you're traversing in this direction, in AC direction, to get to V1 plus del V equipotential surface, starting from the bottom equipotential surface, you are getting a higher value of the rate of change. So this will be the direction of the maximum spatial rate of change, and this will give you the value of the maximum rate of change, okay? So if we write it as dv divided by dn and associated with a unit vector directed towards the AC direction, we will get what is called the gradient of V. Basically, dv/dl is also a rate of change of the scalar potential V. Depending on the value of dl, you will get a higher value of dv by dl or a lower value of dv by dl. So basically, the maximum value of dv by dl is the value dv dn, and this is the magnitude of gradient, and this over here is the direction of the gradients. So gradient is basically an operator on a scalar, and it gives you a vector as a result. Okay, so this is an important part. Gradient is an operator that is always applied on a scalar, and it gives you a vector that denotes the maximum rate of change of the scalar and the direction you have to traverse to get that maximum rate of change. Okay, this operator over here is written by this notation that is called nabla, or this is called the del operator. Okay, this is basically a differential operator. You know, ddx is an operator. For example, ddx is an operator which, if applied on x cubed, will give you a 3x squared as a result. Similarly, nabla is called the del operator, um, which is basically a differential operator associated with the spatial variables. Okay, so ddn over here has something to do with the space variables. So nabla is a vector operator, uh, which is defined as ddl1 au1, ddl2 au2, and ddl3 au3. Okay, so let's say we're talking about the Cartesian coordinate system, then in that case the nabla operator will be dl1 will be h1 du1. Okay, if you remember correctly, then the differential length change associated with each of the axes were denoted as a conversion factor times the differential change of that specific variable. So in case of the Cartesian system, the dl1 will be 1 into dx, right? So alternatively, we can write it as ddx ax plus ddy ay plus ddz az. So here we are using the partial differential notation because there are three variables at play. Okay. In case of the cylindrical system, however, the del operator will look like ddr plus d. There's the catch. If you remember correctly, then dl2 in case of the cylindrical system contains of a conversion factor r and the differential change of phi. So r d phi a phi and d dz a z. All right. If you apply this operator on a scalar, then you individually apply each of these three operators onto the scalar, right? So you're getting a dvdl1, dvdl2, and dvdl3. This will not be as straightforward as this in case of the divergence and curl quantities, but we'll see about that later. Let's say you have a scalar quantity v over here that is used here, and you want to calculate the gradient of this scalar quantity. So the gradient of v is written as nabla v. Okay, and by using nabla, you're basically applying this operator over here onto the scalar quantity. Okay, So the general formula of gradient of a scalar or nabla V is given by dv dvh1 du1 au1 dvh2 du2 au2 dvh3 du3 au3. All right, so this is the formula that we'll be using to calculate gradient of a scalar. So in case of the Cartesian system, the formula of gradient then stands as dv dx ax, dv dy ay, and dv dz az. In case of the cylindrical system, however, the formula looks like this. So you can guess how this formula will look like in case of the spherical system, okay? So del V equal to dv dr ar dv r d theta a theta and dv r sine theta d phi a phi. All right? So these three equations will be used to calculate the gradient of a scalar quantity in different coordinate systems. Rather than keeping in mind separately these three formula, we can just memorize this one thing to replace h1, h2, h3, and u1, u2, u3 according to the coordinate system that we chose. All right, so these will be the things that we'll need.